Hi, my name is Dale McDonald. I'm the lead developer for the synthetic geometry team here at Wolfram Research. Along with my colleagues Peter Behrens, Xiaofan Zhang, and Jack Heimrath, we're going to talk to you about the progress we've made in automated planar geometry. So I will talk about the resource function geometric solve that can be found in the Wolfram function repository. Peter Behrens will show the latest progress on the upcoming fine geometric proof function, which produces human-readable proofs of synthetic geometry statements from geometric scene objects. Xiaofan Zhang will talk about the geometric scene input tool, which is a collaboration with Jeremy Stratton-Smith and gives users an interactive way to select geometric figures and relations to build a geometric scene. She will also give an update on the progress of the computable Euclid site. And Jack Heimrath will talk about our new geometric theorem proving functionality based on the area method. But first, I'm going to quickly talk about this resource function geometric solve. So we can load it by just evaluating this resource function. And so geometric solve basically allows you to solve for quantities related to a given geometric scene. So here, if we have a geometric scene with the right triangle, so we've got vertices A, B, and C, and the vertex at B is a right angle, and we've got the distance between A and B is 3, and the distance between B and C is 4. We want to figure out the distance between A and C. So this is the classic 3, 4, 5 right triangle, and indeed we see that the distance between A and C is 5. So another example is if we've got a triangle with the vertices given except for the x coordinate for this point C, which will give value D, and we want to know the area of this polygon, which obviously will depend on D. And it can solve that. So the area of this polygon is 2 times D. So if we've got an actual geometric scene, so here we'll create one, our good old Bailey's theorem. We've got a triangle ABC, the circle going through the vertices of the triangle, and we specify that the one side of the triangle has to go through the center D of the circle. And if we want to find information about the scene, say the solve for the point A, or the distance between the points A and C, and the area of this triangle, we can do all of those at once for this particular scene. And so we've got the coordinates for A, the actual distance between A and C in this scene, and the area of the triangle in this scene. Right, so that's that function is, again, currently in the Wolfram function repository. And now I will hand things over to my colleagues. Thank you.
Hi, my name is Peter Behrens, and I'll be talking about the function find geometric proof, which is soon to be released as a resource function, which finds synthetic proofs for geometry in our new geometric scene language that can be understood even by 9th grade geometry students. As a first example, we can use Thales' theorem, which states that an angle with subtends a diameter is always 90 degrees. So we make a geometric scene with a circle in it, centered at O, and a line through that center. And we can use random instance to visualize it. And then we can run find geometric proof And the first argument is what we'd like to find, which is the angle at B, and we'd like to find a numeric value of it. So we can use patterns or literal things in the first argument. If we run that, we get proof object, which has a lot of properties to it. And the most interesting of which probably is the proof notebook, which gives a classic 2-column proof. And in this case, it's just one step. It uses Thales' theorem to find that that angle is half pi. So if we look at all the properties of a proof object, the first 4 are fairly straightforward, and they're listed down here. They're the axioms, which is the geometric scene that we were given. The logic used, which is synthetic geometry, if it could be extended to synthetic geometry with trigonometry. The planar angle, the theorem we wanted to prove, which is the first argument, and the result. And these other properties we'll be seeing a little bit later. So there's 2 usages. You can put the assertion you want to prove in the first argument, and you can also prove all things, which proves all things it can up until the time limit or other limits. It produces a proof object if it manages to prove the assertion, or if you put all in there, and it's pruned to create the shortest possible proof of the desired object. So things which were found but which weren't used in the final proof get pruned away. These are all the options. You can see you can control it in many different ways. You can control degrees or radians and many other things. So a more challenging proof would be to find the golden ratio from the classic nested triangles and nested rectangles rather. So we assert that 2 rectangles are similar, and we have to assert that the sides are parallel. So it's a parallelogram, and we also need to give that at least one angle is 90 degrees, so we know they're rectangles. And we want to find the golden ratio, which is this number, and we run it through find geometric proof. We want something equaling 1 over the golden ratio, and we get a lot of things. C1 is the constant of similarity that we created, and finally we find all the lengths and the constant of similarity, which is 1 over the golden ratio. We can use the property proof graph manipulate to show the proof graph, which has a lot of interesting features like tooltips, which show the facts, and if you hover over the edges, they show the proof of the end of the arrows. We can also show we can find relationships between areas after concluding similarity. If we're given similarity rather in a couple angles, we can first find the similarity constant given one of the lengths, and then we can use that to find the relationship between areas. And we can even prove something which is a consequence of the facts that we were given using resolve. So here's an example of using all in the first argument. We have a simple scene with 3 parallel lines and a transverse line. And if we try to prove all, we get pretty much every angle that can be defined using the 6 points there. We can also look at a proof graph, which is different from the proof graph manipulate in that it is actually a graph. If we ask it to prove something that it can't prove, for instance, here we have some lengths in a circle, but we're asked to prove this chord length, which we can't do. It results in a failure object. But there's a lot of good stuff inside the failure object, which is the partial proof and also the augmented scene, which is the scene that you were given, plus everything that it could prove. So if you run random instance on that, you can see a richer diagram with things like the area of this triangle displayed. You can also prove contradictions, as in this case where we have some angles which eventually contradict each other. And we can even put in all kinds of units. Here we have meters and we have inches squared, and we can even ask to prove a length in furlongs and use the result property to get the result in furlongs. Thank you very much.
Hi everyone, my name is Xiaofan Zhang, and I am a geometry developer at Wolfram Alpha. So today I'm going to talk about the brand new geometric scene input tool. And if you can remember from last year, the Computable Euclid website. So the first thing I'm going to talk about is the geometric scene input tool. As you may know, geometric scene is a synthetic way to represent a geometry theorem or a construction. And this tool can help with people that might not be familiar with the syntax of geometric scene and get them started using some interactive selections to produce a scene. And this tool is a collaboration of me and Jeremy Stratton-Smith, and he is from the math content team at Wolfram Alpha. So now I'm going to show this tool with an example of constructing this theorem. So as you can see here, we have a polygon ABC that is cyclic with two diagonals intersecting each other and being perpendicular. And from this point M of intersection, we have a line EF that is also perpendicular to this side BC. So to save us some time, I have already input some of the primitives here. So this first one, you can select the type of the figure, and here input the specific points for the figure. And from the properties, you can add in, select the property. For here, the only one we're using is cyclic. And I'm adding the style to this polygon, and I select it to be orange. So here, these two lines are the diagonals intersecting at point M. And then here is the line EF that goes through point M. And we're also naming these two sides, BC and AD, because we want to specify some other relations between these two sides and the point E and F. So here, I have already put in some of the relations. This is the two diagonals being perpendicular to each other. And then E is on BC and F is on AD. I'm missing one of the relation, so I'm adding it here. So select my figures. So the one we're missing is the line EF being perpendicular to the side BC. Now select the relations being perpendicular. So now we can hit the button, print geometric scene. And this will give you the chunk of code. That's the actual geometric scene. And of course, you can manually insert some other primitives if needed, since we have an extensive collection of geometry representations, and some of them might not be included in our input tool yet, but we're definitely working on that. And then we can also hit this visualize geometric scene button. And then this one will give you a graph that is visualized by random instance of the geometric scene. And this will be easier if you don't like this one, you can just rerun this part of code. And then random instance will generate another graph for you. Okay, this one doesn't look so great. Okay, that looks good. So we're planning to release this input tool later this year, and it will live in WFR, the Wolfram function repository, and potentially in Wayne, that is the Wolfram Alpha Notebook edition. So the second thing I wanted to talk about is the Computable Euclid website, which is a project we've been actively working on. And here I'm just gonna show the design preview. So this is the front page that has all the tiles of each of the books or classes we have. And then from one of these tiles, you can click it and it goes to the class page, which shows a short description of here for book 1, and then for all the propositions that's included in this book/class. And then from one of the proposition tile, when you click on it, it will take you to the proposition page, which definitely contains more information. This is a graph and the statement of this proposition, and we wrote the commentary. And of course, the most important computable version, it's a geometric scene representation of this theorem. And also the dependency graphs, which shows the relationships between this particular theorem and other Euclid theorems. So for the computable Euclid side, we're aiming for a first release next year. So please stay tuned as we work on bringing new and updated geometry projects. Thanks, everyone.
Hello, my name is Jack Highmath, and I'm a consultant with the Wolfram Alpha Math Content team. And today I will be talking about our upcoming area method package for the Wolfram language. And I guess I should first explain what the area method is. So the area method is a semi-algebraic theorem proving procedure for Euclidean geometry. Its main feature is that it generates shorter, more human-readable proofs of many theorems when compared to other mechanical methods. This is achieved by carefully keeping track of the construction steps used when setting up a particular geometric construction, and by only allowing certain conjectures of a specified form, which I will get into later. Points occurring in the conjecture are then eliminated in the reverse order of their construction using appropriate elimination lemmas. And if all of this seems slightly abstract, it should become clear once I explain what geometric quantities, elementary construction steps, and elimination lemmas are. So first, let's talk about geometric quantities. The area method deals with one type of primitive object called points. The set of all points is denoted P, and for all intents and purposes, we may assume that P is just a Euclidean plane. So all our points are coplanar. And then relations between points are expressed in terms of signed distances between 2 points, or signed areas of triangles whose vertices are some 3 points. Furthermore, we also have an important Pythagorean difference function, which measures how far an angle XYZ is from being a right angle. We see that we have this relation that a Pythagorean difference of 3 points is 0 if and only if the angle defined by them is a right angle. And for notational convenience, we also have 2 other quaternary functions, but you don't need to worry about them too much. And with this introduction out of the way, we can define a geometric quantity to be either of the following: a ratio of signed distances, subject to the constraints that the denominator is non-zero, so x, y are distinct, and that the lines through A and B and X and Y are parallel. Otherwise, this ratio doesn't make sense in terms of the area method. Our geometric quantity is a signed area or Pythagorean difference of some points. Next, I will explain what elementary construction steps are. Elementary construction steps, the name is quite self-explanatory, are steps used to construct a geometric or an area method scene. And combined, these steps can be used to reproduce a large subset of classical straight-edge and compass constructions, but they can also be used to make some non-classical constructions, thanks to the fact that the parameters are occurring in some of our elementary construction steps. That can be any real number. So we're essentially working over R instead of the algebraics, as is typically the case in straight-edge and compass constructions. And this makes it possible to, for instance, square the circle. And the 5 elementary construction steps are quite elementary. The first one just introduces a point into the construction. And here I will just mention that the area method scene function just generates a random instance of a construction provided as an argument. Points introduced by the first construction step are called free points. And the points introduced by other construction steps are called constructed or constrained points. And I will use these names throughout the rest of this talk. The second construction step just defines a point y to be the intersection of a line of two other lines. The third construction step defines a point to be a projection of some point onto a line. The fourth construction step defines a point which is on a line through a point parallel to some other line. And the final construction step is somewhat similar, except we replace parallel with perpendicular. And now that we know what the construction steps are, we can define a geometric construction to be a finite list of such elementary construction steps, where in each step Ci, in each construction step Ci, the point introduced in that step must only depend on points constructed, already introduced into the construction, which I hope makes sense. And finally, I will talk about elimination lemmas. I won't list all of them, there are quite a few, but elimination lemmas are used to eliminate all occurrences of constructed, remember that means non-free or points introduced by elementary construction steps 2 through 5, points x from a stated conjecture. And they do this by rewriting geometric quantities in terms of the point x as rational expressions of geometric quantities independent of the point x. And there's actually a unique elimination lemma which can be applied for each combination of geometric quantity and ECS used to introduce a point x. So just to give an example what such an elimination lemma looks like, if we have that y is introduced by the fifth construction step and a and b are arbitrary points, then we can replace the Pythagorean difference in terms of a point y as a rational expression in some geometric quantities which don't depend on the point y. Here you see y does not appear on the right-hand side. Okay, with that out of the way, I would like to demonstrate some examples of our package of proving theorems. So first, I would like to demonstrate the existence of the Euler line, which is the line through the orthocenter, circumcenter, and centroid of a triangle. So we must first define a construction. So we define 3 unconstrained points, A, B, C, and then we define Z to be their centroid, Y to be their circumcenter, and X to be their orthocenter. Next, we can visualize this construction just using the hopefully by now familiar area method scene function. So we have our 3 points A, B, C. We have our points X, Y, and Z. These are our points of interest, and the remaining points are sort of auxiliary points necessary to construct the points X, Y, Z, since the functions is centroid, is circumcenter, and is orthocenter are essentially compositions of elementary construction steps. And now looking at this construction, we might guess some conjectures about the points x, y, z. So we will state 2 conjectures. First, that the points x, y, and z are collinear, and this is the statement of the Euler Line theorem. And we might also guess, although this will probably turn out to be false, that the line through x and y is perpendicular to the line through y and z. So this is how we state our conjectures in terms of the area method. The traditional form here is not necessary. It's just to make the conjectures look nicer. And we might first start by numerically verifying some random instances of our conjecture. So we will generate 20 instances and see if these conjectures hold in those randomly generated scenes. And our first conjecture about collinearity seems to be true, whereas our second conjecture seems to be false. We can also explore these constructions and conjectures visually. So this area method scene explorer function generates a interactive version of the scene, where the points in red are the free points, the unconstrained points, which we can move, and the remaining points we cannot move because they depend on the position of the points A, B, C. And in the top here, we see that x, y, and z are in fact collinear. This is how collinearity is expressed in terms of area method functions. And the lines through x and y and z are not perpendicular. This is all nice. This is all numerical verification. But if we want to generate formal proofs, we can do this using the main function of our package, verify conjecture. We will first try to prove our first conjecture, and hopefully it will turn out to be true. or at least provable. This might take a second. Right, so we have our conjecture at the top here, and the way to read this is that first we eliminate the point x, since if you recall in our construction, x was the last constructed point. Our verified conjecture found an applicable substitution lemma or applicable elimination lemma, and it rewrites this conjecture by applying this elimination lemma wherever it can. And it proceeds by eliminating all constructed points in this fashion, finding all applicable elimination lemmas. And after some work, there are quite a few constructed points, so there are quite a few necessary steps. We find out that our conjecture resolves to true, which is the same as 0 equals 0. So we have found a proof for our theorem. The points x, y, and z, the circumcenter, orthocenter, and circumcenter are in fact collinear. What about the second probably false conjecture? Well, here I took the liberty of pre-computing this result since it takes over 30 seconds, almost 40 seconds. And once again, it's a fairly long proof, which does not result in a true statement. We will see it simplifies to something else. It simplifies to the statement that R1 times R2 is equal to 0. So our statement would be true if at least one of these parameters was 0. So let's see what these parameters are. And could it be the case that sometimes one or both of them are equal to 0? So first, to see what they are, we will just recall what our construction is, and we look for the parameters R1 and R2. And we see that they're just parameters used in defining the points P4 and P6. Now let's see what happens when we set one of them to 0. We just run a dynamic version of our area method scene explorer function. And here we have the parameters R1 and R2. They will appear by default. And what happens if we set one of them to 0? And you see the construction breaks. We get an infinite expression, 1 over 0. So this means if you were to study what exactly this would mean for the construction, that P3 is identified with the point B, and then the line through P3 and B is non-unique, which causes something farther in the construction to fail. Okay, what about some other examples? This is a familiar inequality, and I want to just show this quickly to show that our prover can handle inequalities as well as equalities. So we first construct a triangle, which is just 3 vertices. We state our conjecture, which is stated in this sort of awkward way, because remember, we don't actually have a distance function. And we can only use sign distances when talking about ratios of parallel segments. So we have to express distances using Pythagorean differences. And now we can try to prove this, and we will see that this will quickly resolve to a more familiar form. So once we expand the definition of P, this is a more familiar form of the triangle inequality. And after transitioning to area coordinates, this conjecture turns out to be true. Finally, I have here a pre-computed collection of some theorems, which can all be proved using the area method. And as you see, these proofs are found quite quickly. Some of these theorems are admittedly quite trivial. For example, the triangle inequality or the Pythagorean theorem. These are very simple theorems, but some are quite involved. For example, the existence of the Gauss-Newton line or the proof of Heron's formula. And despite being quite complicated, these proofs are still generated very quickly. Finally, I would like to mention 2 directions in which we plan to extend this package. One is to work in higher dimensions. So for now, we can only prove theorems in 2D Euclidean geometry, but there is, in principle, nothing stopping us from extending this to higher dimensions. And we can also formulate this package in such a way so that it works in different geometries. For example, the Poincare disk seems like a good candidate. And please feel free to reach out to me if you have any ideas on how to extend this package in different directions, things you would like to see. That would be great. I would be happy to take any questions after this talk. Thank you very much for your time.